we can better constrain which of these three regimes is relevant for the formation of various molecules. So, here's some of the chemical pathways necessary for life. Molecular clouds are mostly H2. There's a little bit of carbon and oxygen. The H2 can be ionized by the supernova. When it explodes, it spews out relativistic protons. These relativistic protons whiz through molecular clouds, ionizing the H2, giving you H2+. That reacts with another H2 molecule and forms H3+. H3+ is an acid. It likes to give up its extra proton. So it could react with carbon, for instance, and make CH+ or CH2 singly charged. This is one of the first hydrocarbons. This is the beginning of organic chemistry. This hydrocarbon, in turn, can react with hydrogen, carbon, nitrogen, oxygen, silicon, sulfur, iron, in atomic or molecular form, and eventually lead to complex organic molecules. So it could form carboxy molecules, which to me sounds like something you put in your gas tank. It could form cyanomolecules, which sounds very nasty, and I try to avoid those. Or it can form amino molecules. That sounds pleasant. That sounds good for life. I realize these three words are all jargon, but they're all important molecular chemical families for the origin of life. We have been studying this link in the chemical pathway from atoms in space to molecules. And this is a very highly simplified chemical network that I'm showing. And we're just studying one of the first links in that process. We also look at H3+ reacting with oxygen, leading to OH+ and H2O+. These are precursors to water. They can react with H2 and electrons, and ultimately they'll lead to water. We've been looking at this link in that pathway. So let me describe the experiment. This is the apparatus. How much do you think this cost? There was 1.5 million. It's less than that, but you were close. Other thoughts?
4 million.
4 million. Okay. 1.5 million, 1.4 million. Any other thoughts?
3 million.
3 million. All right, we're getting closer. This was $2 million. Actually, the program that I applied to would not fund anything above $2 million, so I asked for $1,999,978. I wanted to avoid sticker shock. Okay, this is the source that we use to make our C- and our O-. We extract out a beam of either C- or O-. We bend it 90 degrees. A lot of the technology is similar to what I showed earlier. Here's our laser. It's in a light tight box. We send the laser beam across the ion beam, and we convert about 2 to 4% of the carbon or oxygen into neutral atoms. So the green is the neutral carbon or oxygen beam, and then we electrostatically get rid of the C- or the O- because we don't need it anymore. We have a second ion source here that we use to make H3+. We extract a beam of H3+, and we merge it onto our neutral beam. Again, this is like fast cars on the highway. Because they're co-propagating, we can simulate temperatures as low as 25 Kelvin. Not quite as cold as tonight. Actually, much colder than tonight. But in the overlap region, that's where the chemistry happens. And at the end of the interaction region, we direct the daughter products into a detector, and we collect signal. So this is the crew responsible. Ken's been critical for helping to design and develop a lot of the apparatus.